Hello, welcome everyone to Zahid's data mining channel again. This is Zahid Islam from School of Computing and Mathematics, Charles Sturt University, Australia. You can learn a little bit more about me from my webpage at this URL, and today I am going to talk about forest CERN, a decision forest algorithm. And this is the full link of the full reference of the paper. You can actually download that paper from this URL, and if anybody has any problem downloading the paper, please feel free to email me. My name is Zahid Islam, and if you visit my webpage, you can find my email address, etc. Feel free to email me so I can send you the paper. Now, obviously, the very first question is, what is a decision forest? Forest CERN is a decision forest algorithm, but first we need to understand what is a decision forest. Simply speaking, decision forest is a set of decision trees. It is an ensemble of a number of decision trees. For example, in this figure, you can see that there are three decision trees. This is the leftmost one, or the first decision tree. Then you have another decision tree in the middle, and you have a decision tree on the right as well. So as a whole, the combination of all these decision trees can be called a decision forest. Now then the obvious question will be, what is a decision tree? Okay, a decision forest is an ensemble of decision trees, but what is a tree? A decision tree is something like this, which is a tree-like structure, and you can build a decision tree from a dataset in order to learn more information about the dataset, in order to extract knowledge from the dataset. Now, the question is, what is a dataset? A dataset is a two-dimensional table. By a dataset, we mean a two-dimensional table like this. Here we are showing an example of a dataset, an example dataset, and let's assume this is a dataset of a soccer club where you can see there are 12 records or rows. Each record or row is, in this case, is storing information about a soccer match. And there are quite a few columns or attributes or features where each feature actually provides or stores some information of a soccer match. For example, game ID 1 means the match number 1, and there are some information about this game or this match where we can see that the game was played at the home ground, goalkeeper was Matt, weather was dry, there were 20,000 approximately crowd, and finally the result of that match was lost. So this soccer club lost the match. But in the whole dataset, you can see there are quite a few wins and losses, right? Sometimes they win, sometimes they lose. Now, if, for example, they want to understand, the management want to understand, the coach wants to understand that why sometimes we are winning and losing. What is the pattern there? Now, for a big data set, it is very difficult to find out the pattern by plain eyes, by plain understanding or analysis, and that's the place where a decision tree can actually be very helpful. There are many decision tree algorithms existing, for example, C4.5, C5, CART, Explore, etc. And you can actually build a decision tree by using those algorithms completely automatically from a dataset. You do not need to have any pre-assumed knowledge about a dataset or about the pattern of a dataset, unlike many traditional data analysis approaches. And then you can build a decision tree. For example, here we can build a toy decision tree from the toy dataset, and the decision tree will give you a lot of information or knowledge about the dataset. For example, here we can see if the venue is home and the goalkeeper is Matt, then the result of the dataset, the result of the match of the games in the dataset is lost. Okay, so there are two occasions when they played in the home ground having Matt as the goalkeeper and they lost the match. And this is how we can see when they're winning and when they're losing, and possibly the coach or the management can actually learn the pattern of wins and losses. This is a decision tree. Now, the question is, okay, we understand what is a decision tree. We understand that how to use a decision tree, and we also understand what is a decision forest. But now the obvious next question is how to build a decision forest. Now, there are many existing techniques and approaches that can be used to build a decision forest. For example, bagging is a very well-known decision forest algorithm or technique that works as follows. So this is your original dataset. Now, from the original dataset, bagging first creates a number of bootstrap samples. What is a bootstrap sample? A number of sub datasets or number of versions of the original dataset. How does it do that? It actually randomly extracts or randomly selects the same number of records from the original dataset to create the first bootstrap sample. So when it is randomly selecting a record with replacement, what it does, it actually creates the same size dataset where some of the records are duplicated and some of the records are not taken into or deleted or not used. And that's how it creates its first bootstrap sample. When it has its first bootstrap sample, then it can use any existing decision tree algorithm to create the first tree. And then it can continue on to create from the original dataset the second bootstrap sample, and from the second bootstrap sample it can create the second tree. And this is how it can keep on creating bootstrap samples and decision trees. And there you go. You have a set of decision trees, and you can then use those decision trees as an ensemble of decision tree and a forest. Now, there are many other forest building approaches as well. For example, this is called random subspace algorithm, and there is a technique called random forest algorithm, and these all techniques are kind of similar to each other. The goal here is to create a forest. Random forest is actually a combination of random subspace and bagging. Now, there are actually some drawbacks or limitations of the existing techniques, and some advantages of the existing techniques as well. For the main thing here is that these decision forest algorithms are trying to actually build a number of decision trees, and in order to, why they are building a number of decision trees? Because they want to achieve high accuracy, high prediction accuracy for a future record. For example, a future match, if they know all the information like venue will be home, goalkeeper will be Matt, and blah blah blah, then they want to be able to predict the result from the past experience. That's the purpose of building the decision forest. And they want to increase the accuracy, and that's the purpose why they build a forest instead of a tree, because a tree has a certain level of accuracy, certain degree of accuracy, but by building a forest they want to achieve more accuracy. Now, in order to achieve higher accuracy, we observed, and it's a common knowledge, that people generally want diverse trees. So the trees should be very different from each other in the set, and at the same time the trees should be as accurate as possible, very high accuracy. Each tree of the ensemble of the set should be very accurate. So the trees should be diverse and the trees should be accurate. In bagging, you can see the only source of diversity is the bootstrap samples, that the data sets are different, and that's why the trees will be slightly different. In random subspace, there are more diversity because they pick a subset of the attributes randomly, but then the accuracy may suffer, because if you choose a subset of attributes where the set of that subset is not good enough, there are not enough number of good attributes in that subset, then the accuracy will suffer, and so on. So therefore, we propose a technique called forest CERN, and that's our main proposed technique. Here there are mainly two steps. In addition to having bootstrap samples as bagging, we have two more steps. One is weight assignment, another one is weight release. So what we do, we first build a decision tree from the first bootstrap sample as usual, and then we assign a weight to the root attribute, the attribute that is being tested at the root, as 1 over m. M is the size of the number of features or attributes in the dataset. So what happens with this weight, that next time for building a second tree from the second bootstrap sample, we actually calculate the gain ratio or Gini, whatever the criteria, selection criteria for choosing an attribute as usual, but then we multiply that by 1 over m for the attribute AI, right? The attribute that was tested in the first place. So that's why that attribute is actually heavily disadvantaged in the second tree, and therefore the chance of that attribute being selected again is very low. So therefore we are highly likely to get a second attribute to be chosen at the root attribute, at the root node of the second tree, and therefore we are likely to get a very different tree. But then for building the third tree, what we do is we also have a weight release mechanism. For example, the attribute AI, because it has not been tested in the second tree, we actually release a little bit of weight of it. That is we add again 1 over m weight to its original weight. So for building the third tree, the weight of AI, attribute AI, is then 2 over m, and because the attribute AJ has been tested at the root of the most recent tree, then the weight remains for attribute AJ as 1 over m. And with this weight combination, we then build the third tree. Say for example, in the third tree, we choose the attribute AK. And then the weight for the attribute AK, that is WK, will be 1 over m, and this weight will be used for building the fourth tree. Whereas the weight of AI, the attribute AI, will now increase to 3 over m. And this is the whole mechanism of forest CERN. The simplicity is its strength. It's very simple, but at the same time it is likely to give you very high diversity. And the trees will be very diverse, and the trees will be very accurate, reasonably accurate. We actually then run many experiments on quite a few publicly available datasets, and we check the ensemble accuracy of forest CERN with many existing techniques: random forest, random subspace, bagging. These are the main well-known techniques in the literature, and we find that forest CERN achieves very high accuracy. Not only that, we also check its diversity and its individual accuracy. As I said before, this is what we try to achieve: high diversity and high accuracy, and we see that forest CERN gives the most diverse forest, and its accuracy is also very high. We also do some statistical analysis, and we find that the results are statistically significant. Now, the paper is available, as I said before, in this link. If anybody facing problem downloading the paper for whatever reason, please feel free to email me. This is my email address, zahidislam@csu.edu.au, zislam@csu.edu.au, and I will try to send the paper as soon as possible to you, an author's copy of the paper. And the Java code, we are making our code available in our web page, which is here. If the code, this forest CERN code, is again not available there, feel free to email me. On request, we will send you the paper. Thanks for watching. Enjoy your time.